This question is also on coherence. This time it is on coherence length. So we have exercise 2.6. This says compare the maximum path differences that will give rise to fringes in a Michelson interferometer when using the following two situations. So the first one is when using the 546.1 nanometer line from a Doppler broadened mercury lamp operating at 150 degrees centigrade The next one is the light from a stabilized helium neon laser with a line width of 1 megahertz operating at 632.8 nanometers. So in this question we basically have to find out the coherence length, because in any given interferometer we would see fringes only when the path difference is less than or equal to the coherence length. If the path differences exceed the coherence length, then we will no longer see fringes. So let me write that condition down. We see fringes only when path difference is less than equal to coherence length. So this is an important point. So let us now find out the coherence lengths for the given two cases that we have. The first case is of Doppler broadened line. We saw Doppler broadening in the last question as well. So let me rewrite the formula for the Doppler broadening. See, in the previous case also we had this Doppler broadening. So I will rewrite it over here. For Doppler broadening, so in this expression, lambda is wavelength, kb is Boltzmann constant, T is the temperature, M is the mass of atom, delta W is the spectral width. So let us write down the values that we have. Wavelength for our case is 546.1 nanometer. Boltzmann constant is 1.38 into 10 to the power minus 23 meter squared kg per second squared Kelvin. Temperature is 150 degrees Celsius, but we want temperature in Kelvin. So for temperature in Kelvin, we add 273. So temperature in Kelvin is 150 plus 273 Kelvin, which is nothing but 423 Kelvin. Mass of the atom, we are using mercury lamp, so we want to find the mass of one mercury atom. So mass is 200.59 grams per mole. So 1 mole of mercury atoms would weigh 200.59 grams. Now in 1 mole we have Na, that is the Avogadro number of atoms, which is 6.022 into 10 to the power 23. So Na number of atoms would weigh 200.59 grams. So we can find mass of one atom. So we can find out the mass of one mercury atom from this. So that would just be, if 6.022 into 10 to the power 23 atoms have the mass 200.59 grams, then we can find out the mass of one atom from here. So this is the spectral width for the case of Doppler broadening. From this we will get the coherence time. So we will get coherence time. This again, we saw this equation last time. So this is the coherence time. So let us put the expression for delta omega. So ln2 inside the square root cancels out. This gives us I forgot, there will be one root m in the numerator because of this m over here. So this is the expression for coherence time. Tau c is coherence time. From this we can find out. So once we will have the coherence time, we can find out the length, the path difference that would give us the rise to fringes. This is the question that we have. So now we can find out the coherence length. So coherence length is nothing but speed of light times the coherence time. So if we put in the above expression, we get this, and plugging in the values for all the constants that we have, we get roughly 34.9 centimeters. This is the coherence length, LC coherence length. Now for fringes, the path difference should be less than equal to the coherence length. The next part is for helium neon laser. So this is for finding the coherence length of helium neon laser. So for helium neon laser, we are given the wavelength, helium neon. The wavelength is 632.8 nanometer. Line width is 1 megahertz. It is given. This is nothing but the frequency width. From this we will get the spectral width. Spectral width is 2 pi times delta nu. This is because omega is 2 pi times nu. So d omega is equal to 2 pi d nu. So delta omega is 2 pi delta nu. And from this we get coherence time tau c as 1 over delta omega. We calculate, this comes out roughly 1.59 into 10 to the power minus 7 seconds. And from this again LC we can calculate the coherence length is c times the coherence time, and this is roughly of the order of 47.75 meters. So this solves the problem. Notice how big big number we get for the coherence length of a laser. It is 47.75 meters roughly, so of this order. So it is more than 40 meters. That means that it is going to be much easier to obtain fringes, interference fringes in a Michelson interferometer if we use helium neon laser. Even the mercury vapor lamp has a pretty decent coherence length of about 35 centimeters. So we can easily get fringes from the mercury vapor lamp as well. Incoherent sources, typically, let's say sunlight, for example, would have a coherence length in the range of micrometers. So it would be very difficult to obtain fringes from such a source. So this brings us to the end of this question.